Once we get away from working on a number line and start looking at items in a two-dimensional space, midpoint and distance become very important and a little bit different in being able to calculate and find their values. So in this lesson we're going to take a look at how to find the midpoint and distance both for a number line, which will be review, and in a two-dimensional plane or in a coordinate grid system. So first off, formulas. The midpoint for a one-dimensional system is found with the formula that was given earlier of simply taking our point A location, adding the point B location, and dividing by 2. That same idea in a two-dimensional system, where we have both x and y to deal with, our midpoint becomes the average of the x's, so we're going to say x1 and x2 divided by 2, and then the average of our y's, so y1 plus y2 divided by 2. And when we have the subscripts of 1 and 2, it simply means the first one, or whatever we designate as point 1, and then the second one. Now for distance, again, review, distance for our one-dimensional system is equal to the absolute value of wherever location A is minus location B. And the reason we do absolute value again is because it is always a positive number for distance. Now the distance formula for a two-dimensional system is a bit complicated, and when we get into working with it I'll break it down a little bit more, but the distance is equal to finding the difference of the x's, so we'll go x1 minus x2 and square it, the difference of the y's, y1 minus y2 and square it, add them together, and then take the square root of the entire system. Now again, this looks very complicated, but once we get into using it you'll see it breaks down pretty nicely. So let's get some practice using it. When we are working with midpoint, we can work in both one-dimensional and two-dimensional systems. So in order to get started, we simply need to select a pair of points. So if I put point A at -1 and point B at 5, how do we find the midpoint? Again, midpoint is simply the average of these values. So our midpoint M is going to be equal to A plus B divided by 2. So in this case it'll be -1 plus 5 divided by 2. -1 plus 5 is 4. 4 divided by 2 is 2. So I can place at location 2 a point that I call M. And if you look, from A to M is 3 units, from M to B is 3 units. So M sits in the middle, hence the term midpoint. But what happens if we were to change this a little bit and say that point A, the length of AB is 15 units, and A is located at 5. The midpoint M is located at -2.5. How would we find B? Well, we know that the length is 15, so if we go from 5 to -2.5, we're moving left. We would continue to move left, and we would end up another 7.5 units away. B is at the location -10. So we can take these ideas from a one-dimensional system and put them out into a two. Let's place on our grid here, with the scale of 1, A at -2, 5, and B at 3, -1. Now we need to find the midpoint. Again, our midpoint M is calculated using the difference of our x's, the average of our x's, and then the average of our y's. So, for the x's, our locations again are -2, 5, and 3, -1. So we're going to take -2 and add 3 divided by 2, and then we will take 5 and -1 and divide that by 2. Well, -2 plus 3 is 1, and 5 plus -1 is 4. Finding the average of these, we will get 1/2, 2 as the location of m. So we go right half a unit and up 2 to this location here, and there is m. You'll see that they do form a linear set, and visual approximations, m is halfway in between a and b. Using the same system, we could be given location a and then location m and use the patterns to find b. But let's take a little bit of time to calculate distance. Now, as I had said before, the distance formula looks rather long and complicated and intimidating, but it's not really as bad as it seems. So let's break it down into its pieces and see what we can find. What we're doing here is we're trying to find d, which is the distance, direct distance between these 2 points. Now, in order to do this, we use this formula, which tells us that d is equal to this large square root of items being added together. So what are those items? First, we have x1 minus x2. And what that does is it says if I start here and go to here, what is that horizontal change? That is, again, x1 minus x2. Some people put x2 minus x1. Ultimately, it won't matter because what we do is we take this distance and we square it. So if it was positive, it'll remain positive. If it is negative, negative times a negative becomes positive. Next, we go y1 minus y2, which is telling us if we start here and end here, what is that vertical change in distance? And again, it doesn't matter which one you put first, because we're going to take that and square it, and then we take the square root. Now, this formula looks much more complicated than it should be, simply because by making the distance formula in this manner, you can see that we have formed a right triangle. And from algebra, you should have learned something called the Pythagorean theorem, which tells us that if you need to find the distance between 2 points, take the 2 legs, the 2 parts that make the right angle, take their distances, which were called A and B, square them, and add them together, and it'll equal the square of the third side, which was called C. Well, what we have here is simply a glorified formula that explains the Pythagorean theorem. So using these points that we have here, let's actually find this distance. This point was -2, 5, and this point was 3, -1. So using the simplified version, how far is it horizontally from -2 to +3? And that distance is 5. So we're going to take our 5 and square it. To that, we will add our horizontal change. How far is it from 5 to -1? If we start at 5 and go to -1, that change is down 6, and we will square it. Then we will take the square root. 5 squared is 25, 6 squared, or negative 6 squared is 36, and we're going to be taking the square root of that. So what we get here is the square root of 61. Now 8 times 8 is 64, so we should be looking a little bit smaller than 64 in this. And using decimal approximations to the nearest hundredth, we come out at 7 81/100ths for that distance. So we could go through the formality of using the formula, or we can use what it means and realize it is just Pythagorean theorem. So midpoint and distance are going to be important as we move away from general formulas and start working on coordinate planes. So make sure you have these ideas down and are ready to use them.